coordinate system. The main one is the one depicted here, and if you can, you want to drop the lights a little bit there?
Now
Thanks.
just dealing with audio stuff.
Thanks. Okay, so you can see there's a whole lot of lines marked on this sphere, and probably the important one we'll start with is the green one, which is the equator. And this is the same as the equator on the Earth, so it's basically the point on the Earth that's furthest from the poles. So when the Earth is spinning around, the equator's in the middle, and we can project that onto the sky and use that without any real modification to locate objects either north or south of the equator. The difference is on the Earth that's called latitude, but in the sky it's called declination. But it's basically the same measurement, measured from the centre of the Earth relative to the equator. Shown there is declination and the green angle there. And then the other coordinate is obviously going around east-west. And the way we do that is to use on the sky, instead of longitude, which is basically attached to a point on the Earth in Greenwich. That's sort of political reasons going back a few hundred years, the reason why Greenwich is the origin. But for the sky, you can't use a point on the Earth because obviously from any point on the Earth, you look up, the stars are moving all the time from rising and setting. So you can't just project longitude onto the sky and use that as a coordinate system. We need a similar idea, but we need some way to figure out an origin. And the way that it was done was to use one of the crossing points of the equator, which is already mentioned, in the ecliptic. So if you don't know, the ecliptic is the path of the sun through the year. And so twice a year, the ecliptic crosses the equator. One is called the vernal equinox, which is the northern hemisphere spring, and the other one is the autumnal equinox, which is spring for us, in fact. But so we use that point on the sky as the 0 point for longitude. And instead of measuring an angle around that right ascension, we measure in time. And it's not the same time as you use on a clock, which is solar time, mean solar time. For the sky, we use what's called sidereal time. And the difference is just under 4 minutes each day. So if you have a look at stars rising and you time them rising each night, you'll see that they rise 3 minutes and 56 seconds earlier each night. And that's caused by the motion of the Earth around the sun. So once you've completed a full year, if you multiply out that 3 minutes 56 seconds by 365 and a quarter days, you get back to where you started. Okay, so yeah, we can also, right ascension isn't very convenient for you locally. So quite often you'll see in planetarium programs, they'll tell you the right ascension and declination of a star or planet or whatever the object is, but they also give another value called the hour angle, and that tells you how long until the object is reaching your local meridian or how long it's past the meridian, depending on different programs actually do it different ways. Some do it plus or minus 12 hours and some go 0 to 24. So in the plus or minus scheme, an hour angle of 3 hours means that the object is 3 hours past the meridian, so it crossed the meridian 3 hours ago. The meridian is just the north-south line that passes directly over your head. Okay, so so you will often see this for your local location, hour angle, rather than right ascension. But declination works anywhere, so that's not a problem. Okay, so if we go back in history, I think there were probably attempts to map the sky before this chap Hipparchus. but he was pretty influential because he had a catalogue of 1,000 stars that he could observe from, where was he located? Was it Alexandria? Does anyone know? Yeah, so obviously they can't see into the far south from there. His star catalogue had a lot of influence on a guy called Claudius Ptolemy, who worked out a system for the motion of the planets that sort of held sway until the time of Copernicus. So he actually came up with another idea as well, which I'll mention further along. But he is probably one of the most famous astronomers of ancient history. Okay, now before we move on, we do have a problem with the coordinate system that we've chosen, right ascension and declination. In fact, the guy I just mentioned, Hipparchus, discovered this problem, and what it is that the Earth's axis is not fixed. The Earth wobbles around like a top, and by looking at what were ancient hymn records from Babylon, he was able to work out that this coordinate system wasn't staying consistent, and he figured out that it must be because the Earth's axis of rotation was itself rotating like a top. And you can see here that the poles trace out a circle, and it takes about 25,000 years or so to do that rotation. So it's a fairly slow change, but just by using measurements that had been taken centuries before his time, he was able to work out that this was happening. So this is an immediate problem for our catalogues, because if you specify the coordinates of a star, the problem is only valid for a particular date. And so it turns out it's not a problem these days, because your planetarium software will automatically do the calculation to precess the coordinates to the current date. Okay. Right. Another interesting catalogue is the Uranometria one by Bayer, who had, as you can see, had all these plates, metallic plates made up with stars showing the positions of stars, but he also had this artwork representing the constellations. And a lot of these constellations go back to probably fairly ancient times, but he did invent a few as well. And some of the inventions came from Dutch navigators that travelled to the southern hemisphere. But they're quite beautiful illustrations. I think I've seen a book with them all printed in it. But he didn't really have a good knowledge of the southern hemisphere, so the whole of the southern hemisphere got put onto this single plate. And you can see there's some unusual things here, sort of animals that have been discovered in what they call the New World, fish and other things like that. So we come to more modern times, the International Astronomical Union, and they made an arbitrary decision that they would divide the sky into 88 constellations, trying to keep with the sort of traditional Roman, Greek, Persian type and Arabic ideas. So they don't recognise sort of different cultures around the world, unfortunately, but I guess you need some system. So if you have a look at them, rather than just patterns of stars, if you fire up your probe planetarium software, you can usually tell it to draw the constellation boundaries, and you'll see that they're all straight lines. And the reason this was done was that they could define the boundaries of the constellations in terms of constant declination or constant right ascension. So that's how that came about. The boundary system was invented by this guy Eugene Delport. So just as an example of that, we'll have a look at Orion. You can see the constellation boundaries there. And it's all of these straight line segments. And they tried to fit all the stars that were officially associated with Orion. You notice the bit up there, which is supposed to be the club of Orion the Hunter and so on. So that's the reason for that bit going up there. And they have to come down to include Rigel and Safe. But this is another amusing thing to do with your planetarium software. Bring up the constellation boundaries and say look at Orion or any other constellation will do, and then go 5,000 years into the future, and you'll find that all of these lines have actually been rotated. So that's because of precession as well. So there is a bit of a flaw in the plan. Okay, these are the constellations. Everyone here can remember them, of course. Okay, so you have the three-letter, all of them have got three-letter codes, like Crew for Crux, Door for Dorado, and so on. The way that, because these are, the names are actually based on Latin, so if you have a star that is in a particular constellation, you don't say, for example, Alpha Capricornus. The proper way is to use the Latin genitive, so you'd say Alpha Capricorni, and similar for Crux, you don't say Alpha Crux, you'd say Alpha Crucis. So I guess the genitive indicates possession. So basically, the star Alpha of Crux would be Alpha Crucis, and the same for all of them. Some of the endings, unless you've heard them before, are pretty hard to guess. Like for octans, it's octantus. Okay, so we'll move on from that stuff on to the catalogues. And basically, there's some obvious what information you'd be looking for. If the star is one of the brighter ones, it'll probably have a proper name, such as Sirius or Rigel, those kind of things. And then they'll have an ID that is unique to the catalogue in question. For example, the Bayer, the Flamsteed number. If it's the modern Gaia catalogue, it has a little big telephone number. That catalogue has got well over 1 billion stars in it.
You use the SAO catalogue.
The Smithsonian one.
Yeah.
Yeah.
About, I think it's about 1,000 bright stars north of declination -20.
Okay. Yeah, so, and obviously there's a lot of other information we want in the catalogue. We've got the brightness of the star, its parallax, which is the astronomical way of specifying how far away the star is from us. There's other things. We can have spectral type, proper motion, radial motion, all sorts of anything you can measure basically. If you're not sure what proper motion is, when it used to be believed in the old times that the stars never move, they're all fixed in the sky relative to each other. So every year they'd come back and everything was exactly the same. But when you look with precision, it's obvious that the stars are actually all in motion as well. Because they're so far away, the motion to us appears to be really slow. But with modern telescopes and systems such as the Gaia satellite, the proper motion can be measured to quite high accuracy. And that's the actual motion of the star across the sky as we observe. So, for example, stars that are closer to us will tend to have a higher proper motion. But they can also have a radial motion, which means motion towards us or away. And we can measure that using Doppler shift in the spectra of the star. As far as proper names go, they're mostly derived, Arabic derived or Latin derived. the IAU approved 227 star names, and that was as at 2016 working group that was established. And the visual magnitude ranges from minus 1.44 Sirius to the faintest one, which you can't see with the naked eye. Seems a bit weird, Proxima Centauri. But the reason that was given a proper name is just because it's the closest star to us. So they decided it should have a proper name. And quite a lot of people were referring to it as that as well. Okay, Bayer designation, which you'll come across. So this scheme was the brightness order within the constellation. So start using the Greek alphabet, the brightest star in Orion, Alpha Orionis, despite the fact that because Betelgeuse is a variable, sometimes Rigel is brighter and sometimes Betelgeuse is brighter, so it doesn't hold exactly. And then Flamsteed, who was the first astronomer royal in the UK, his catalogue has stars numbered in right ascension order within any constellation. So you'll see this one, you might hear of a star called 22 Eridani, that kind of thing, where they use a numeric rather than the Greek alphabet. All of these only apply to the bright stars that were pretty much known pre-telescope or the very early primitive telescopes. Okay, so obviously the position we've already talked about. So the east-west is the right ascension and the north-south is the declination. And as we mentioned, the catalogue has to say the date on which these coordinates were true, and that's referred to as the epoch. And usually what the IAU do is declare a particular base date, and it might be the most recent one I think was J2000, but I think there should be a new one this year, J 2025. So they republish all of the right ascension coordinates when they put out new catalogues. Is it 50? Okay, yeah. Oh, so we won't get a new one until 2050 then.
Yeah, I know there was
2000 was the last one. Yeah, I couldn't remember it was 25 or 50 years. But obviously, if you're using computer software, you don't need to do that calculation. In the old days, up in the Zeiss, when they needed really precise coordinates, they have to calculate the precession themselves using maybe a spreadsheet, because they did have a computer, but none of this planetarium software was available for a desktop PC back in those days. Okay, this is brightness, and if you've not seen it before, brightness of stars seems a little bit weird as to how they do it. And again, it goes back to the ancient Greek astronomer Hipparchus, and what he did in his catalogue, he ranked the stars from brightest to the ones he could just see. So anything with a magnitude 1 is among the brightest stars, and the ones that you can just barely see, he marked as magnitude 6, and then he just divided up between the brightest and the faintest that you could see with the naked eye. And for historical reasons, they decided to keep with the system, but put it on a more scientific basis. So there's obviously a lot of things that are much brighter than a first magnitude star, such as the sun. So we have to go into negative numbers. Even things like Venus has a negative brightness. So the sun's brightness is a bit over minus 26 on the scale. And then at the other end, you see I've got down to 32. That's about the faintest stars that have been imaged on the Hubble Space Telescope. And you might wonder, well, what's the actual scale? Well, it's actually not a linear scale. So if you have any 5 magnitudes, like the difference between first and sixth, that means the brightness is 100-fold difference. And Pogson came up with that scheme to roughly approximate Hipparchus's scheme. So the difference between one pair of adjacent magnitudes, say first and second, is a brightness difference of just over 2.5. And as seen there, the brightness of Sirius minus 1.46. Okay, so you need some way to calibrate this, obviously, and originally Polaris was used as the baseline for magnitude 2, but then it turns out that Polaris is variable. When that was discovered, they moved to Vega. That's a magnitude 0, but that's slightly variable as well. So they don't use stars now as the method of calibration. They use an absolute flux as measured with a photometer or CCD camera. And then another term that you'll see is absolute magnitude. So what we've been talking about with Hipparchus's magnitudes are how they appear to be. But of course, all of the stars are at different distances. So a really bright star a long way away might be not visible to the naked eye. But a fainter star that's close, you can see it quite easily. So they have this idea of absolute magnitude. And what that is how bright would it appear to be if all the stars were at the same distance. And the distance they arbitrarily chose is 10 parsecs, or 32.6 light years. So if you move all of the stars to that distance and then measure the apparent magnitude, what you're measuring there is now the absolute magnitude. So it's comparing what they would be like at the same distance. Yeah.
Why wasn't Sirius Hipparchus's brightest star?
It was, but he just said, oh, these bright stars are all the first rank. He didn't say, oh, one was a little bit brighter than the others. He didn't go down to that finer detail. He would have realised that Sirius looked brighter than the others, but he didn't rank them down to that level of precision.
So it was more of a histogram of buckets.
Yeah, it's just like a ranking system, yeah. Okay, so now another thing that's important to astronomers you have in the Catalogue of Stars is the spectral class. And this strange system where they go from hottest to coolest, OBA, FGKM. There's various acronyms that you can use to remember the acronym rather. And within each class you can divide it up into subclasses. This system actually came from University of Harvard when they were first doing spectroscopy, and they were incredibly confused. And they started using letters of the alphabet, and then they realised, oh, this doesn't work, and they ended up shuffling them all around. This lady called Annie Cannon actually invented the scheme that they came up with, and so that's stuck to this day. And so yeah, as I said, you can go from type O to 09 or 01. So they're sort of the subdivisions using a number within that spectral class, but they more or less follow temperature. But then they also have a thing called luminosity class, and for example V for main sequence, and that looks at certain characteristics of the spectra of the star, and V actually means dwarf star, so the Sun is a G2V dwarf. You can also have giant stars, supergiants. It's got a list of the various luminosity classes there. It gives some examples, like Arcturus is a luminosity class Roman numeral 3, which is a normal giant, and you can have hypergiants, as it says there. Yeah.
Is it possible to have any luminosity class for the next spectral class, or do they tend to group?
They tend to group, but they can be mixed up as well. Like, for example, you've got white dwarfs is the other one. Obvious one is a type 7 luminosity class, but temperature-wise it would be very hot, something like a B class star. But white dwarfs all vary because over time they cool down, so it depends how old the white dwarf is. So yeah, they do get mixed up.
You've also got on the left-hand side, you've got the W before the O, which is the Wolf-Rayet class.
Yeah. That's they're basically a massive star that's starting to blow off the outer layers of its atmosphere as they're starting to get to the end of their life, and they're burning carbon in their core, that kind of thing.
And after the M, they've also got MRES.
Oh yeah, those ones I don't know they use so much anymore.
Don't they?
Yeah, because they're kind of special cases.
Yeah.
Okay, right. This is just a list of the catalogues that you possibly are likely to come across in your reading, or a lot of the planetarium programs will mention these, or news articles, they'll say such and such a star. There's the Yale Bright Star catalogue, so that only probably about the 6,000 or 7,000 brightest stars goes down to magnitude 6.5, which is the dimmest, down to about the dimmest that you can see on a really dark and moonless night if you've got really good eyesight and you're well away from any city, probably the outback of Australia or somewhere like that. Okay, this one is a bit less common, the BD, but I do see it refer to this catalogue for some reason, but this was another visual catalogue but using telescopes. And the purpose of this catalogue was to establish positions, so it's sort of like a precursor of the modern Gaia catalogue, where the focus was positional information, the most accurate they had for the time. Bonadursch Musterung, which is obviously German origin. And I won't say much more about that. The Henry Draper one is actually related to what we were talking before, spectral classes. The Harvard University, that project that Annie Cannon and Wilhelmina Fleming and others were involved with, was the first photographic catalogue that used spectra. Harvard University did an all-sky survey where they collected stellar spectra and other information using photography. And they used glass plates, and apparently Harvard University still have the original glass plates that have been scanned digitally, so they don't have to be touched anymore, because there's still some useful information on them, because obviously things do change over time, and so they can refer back to the data from those plates about any changes that have occurred with star brightness or positions, anything like that. And so you'll see a lot of stars, HD, something or other. The reason it's Henry Draper is because Henry Draper was an amateur astronomer who was quite wealthy. He was the first person to image the Orion Nebula with a camera. And so he was the first sort of amateur astrophotographer, or even any astrophotographer really. And when he passed away, his widow left a big endowment to Harvard University to do this work, so that's why he's got his name on it. Somebody already mentioned the Smithsonian Astrophysical Observatory catalogue. That's sort of like an updated HD one, another astrometry focused one. And again, the Hipparchus catalogue. The Hipparchus one was a bit of a play on the name of Hipparchus, the ancient Greek astronomer, and forming from the words high precision parallax collecting satellite. So this was the precursor or the forerunner of the Gaia satellite. And its sole purpose was to get above the atmosphere and get accurate position information of stars, which allows you to get the distance, because if you've got accurate position information, you can measure the parallax of the star. The Tycho ones were prepared by the US Naval Observatory, and their focus was mainly actually intended for military navigation and the like, but they were freely available. So they were, for quite a while, their various catalogues were probably the ones that amateur astronomers that were doing any kind of astrometry type work would use their catalogues as a reference. But these catalogues are now getting quite big, until finally we come to the Gaia catalogue mentioned at the bottom there. That one isn't complete yet. Available is what they call Data Release 3. I think Data Release 4 is pretty close to being released. Does anyone know? And I think the final version of the catalogue won't be published until 2030, which is going to be Data Release 5. And so this is the grand master of all catalogues, I guess you could call it. It's another space-based satellite telescope. It actually has 2 telescopes in it and especially designed for really accurate astrometry. And it orbits the Sun out at the Lagrange 2 point, out further out than the orbit of the Moon. And it's been running for over 5 years. I think they've finished the actual measurements now, but they've got a way to go to catch up with all of the processing of the data that it's captured. It's taken measurement of about every star that it can see in the sky about 70 times. So the more times it does the measurement, it helps eliminate errors. The catalogue's freely available, by the way. It's quite big. You can download it for most planetarium programs, the ones that allow you to download specific catalogues anyway. What this image is here, you think, oh, is that a picture of the Milky Way? It's not actually a picture. What somebody has done is taken every point out of or every star in the Gaia catalogue and plotted it. So that's what you end up with. It's so detailed that you end up with an image. There's no nebula in this. This is all stars, but you can see the dark nebula because there are no stars visible at those points, so it shows up the dark nebula. So it's pretty interesting. I presume it'll be done again with when they do the final releases and so on. You can see there the 2 Magellanic Clouds stand out quite well. Okay, now hopefully this will work. This is what somebody else did with the Gaia data. So you've probably, I don't know, has everyone heard of a Hertzsprung-Russell diagram? So what it is measuring the brightness of a star versus its temperature. Now we can't do that directly, the absolute magnitude, so they use what they call a colour magnitude diagram instead. And what somebody did here was to plot this and show that these aren't just static, because you can see all the variable stars as Gaia is observing them over and over again. Their position on the diagram is moving. So it's quite interesting. It's a different, actually I'll play it again as well if it'll do it for me. Oh yeah, here we go. Is it going to redo it or do I have to?
Just go back one slide.
Oh yeah, and go forward again. Hopefully it'll do it for us. Oh, there we go. Yeah, you can see the Cepheid variables, long period variables starting to show up as time goes on. Cataclysmic variables down the bottom here. those are white dwarfs that have basically have a companion star that's dumping material onto an accretion disk. So they have these sudden outbursts. So that's what's being measured there, and all the other variables that it picks up. Yeah, whenever you see these in a box, they're just like a static picture, but there's actually dynamic things going on. Okay, but more on stars. There are, because there's lots of catalogues, and I've only mentioned the more common ones. The problem is you come across a star, like you see there's the HD 29134, and you think, oh, what the heck is that? Well, it turns out this is actually the HD number for the star Aldebaran. And so how the heck do you link all these together? Well, here it is here. This University of Strasbourg in France have a system called Simbad, and you go in and type any catalogue ID or star name, and it'll spit out all of these. So that's how you can link the different catalogues together. So yeah, anyone can access that. Okay, we did. There are special catalogues just of variable stars, and if you look at variable stars, they seem to be named a little bit differently to the others. Or you'll often see, like, for example, stars that have got a letter in their name, like R Coronae Australis is quite a famous one. And so if you see a capital Roman letter, or two letters like that, or the prefix V followed by a number, it indicates that it's a variable star, or a known variable. And so that'll appear in different catalogues of variable stars. So I don't know how the system came up, but they ended up using single letters, then double letters, but they don't use the whole alphabet, so it's kind of strange. So, for example, the letter J is never used, not quite sure why. So if you see those, you know what they are. So that's enough about stars, so we better move on to the deep sky objects. So these are things that are not single stars. They could be clusters of stars, nebulae, or galaxy, or you can get different types of nebulae, of course, emission nebula, dark nebula, reflection nebula, and so on. So across the bottom there's a glossary showing you the symbols that will get used in most planetarium programs or books where they print star maps. And you can see, forget about the colours, that's not significant, it's the shapes. So an ellipse tilted like that is an indication of a galaxy. A dotted circle is an open star cluster. Open star clusters are the clusters that are found in the plane of the Milky Way for the most part, and they're fairly sparse and generally pretty young stars. Then you have your globular clusters, which are very old and have very large numbers of stars in them, could be up to 1 million or more. So they're a circle with a cross. And then you have a planetary nebula. The symbol is a circle with sort of crosshairs outside the circle. If you don't know what a planetary nebula is, it's basically what will eventually happen to the sun when it runs out of fuel. It'll go through a final burning phase in its core, which gets really hot, throw off its atmosphere, and the atmosphere will expand, cool down, and form a planetary nebula, leaving a white dwarf behind. So when you're looking at those, some of them are quite interesting to look at. You've got bright nebula, which are generally nebula that are emitting light under fluorescence caused by ultraviolet radiation from really hot stars, causing the gas in the nebula to fluoresce. And then you've got just a black dot, not usually that big, indicates a star. And if you have a thick circle like that, like a thicker version of the letter O indicates a variable star. So those are the common symbols that are used on star maps, or planetarium programs use those as well. Okay, the catalogues for these are a little bit different. The earliest one we know about for these deep sky objects is the Messier catalogue, and you won't be around astronomy for long before hearing about the Messier catalogue. Just the letter M is used. Now, this was originally not intended to be a catalogue of deep sky objects. It was a catalogue of things that might be mistaken for comets. So that was the purpose of compiling this catalogue from Paris. Charles Messier and his collaborator Pierre Machin. Obviously, this was before the invention of electric lights, because most of these objects you wouldn't be able to see from Paris anymore. Okay, yeah, so there's 110 of them, but because it was the catalogue was done from France, it's very much northern hemisphere centric. Examples you've heard of maybe M11, the wild duck cluster is also known as, M42, and that's the Great Nebula in Orion. Anyone know what M45 is?
The Argus.
Yeah, what else is it known as?
Margariti.
Yeah.
I presume that was the answer you're looking for?
Yeah.
Subaru?
Yeah, Subaru is also.
Well, I'm looking at some of those Messier Messier objects. You sometimes wonder how you would confuse that for a comet.
Well, maybe they didn't have very good optics.
No, I was just thinking of something like M24, the Great Sagittarian Cloud.
Yeah, people didn't really know much about astronomy, so I guess it was helpful to have a list of all the things that, and you know, you're looking at something, oh, I think I've discovered a comet, and then no, sorry, you're out of luck.
I guess there's a lot of objects he actually missed. Didn't put them in.
No.
Did he ever find a comet?
I believe he did, yeah.
I think he got 2 or 3 of them, actually.
Yeah. So this is still useful for amateur astronomers especially, and it's actually possible in the Northern Hemisphere at a certain time of year. I think, is it in the autumn? Does anyone know, where you can actually see? Oh, it's spring. So there's spring. So it's possible to see all of them in one night. You have to basically observe from dusk to dawn. And they actually used to have a thing called a Messier marathon where they try and do that. Right, so this is these are just the images of all the objects in the catalogue. You can see there's all sorts of different things in here. There's galaxies, planetary nebula, star globular clusters, open clusters, all sorts of stuff. Okay, there was a couple of attempts to extend the Messier catalogue to the southern hemisphere. A notable one is what's called the Caldwell catalogue, and this was done by Sir Patrick Moore, and so it basically includes a lot of the things that Messier, obvious things in the northern hemisphere that Messier missed, and as was mentioned before, plus southern hemisphere objects. And so we've ended up with objects that have ended up in multiple catalogues, is the usual story. An example there, Caldwell 106, also has a star designation, 47 Tucanae, and it's also NGC 104. So That's a very the second brightest globular cluster in the sky, which is in the sky position near the Small Magellanic Cloud, so fairly favourite object to view in the southern hemisphere. And then a South African comet hunter also produced a similar southern hemisphere catalogue named the Bennett catalogue. I don't see people using that much, but it is out there.
Oh yeah, it's actually quite a few, it's got quite a few interesting objects in there.
Yeah, I don't see people referencing it a lot though, so maybe that it's people aren't familiar with it. Okay, now we come to probably the, I guess a more important one particularly for professional astronomers, is the new general catalogue of nebulae and clusters of stars. And you can see how new it was, 1888. And basically what happened was this was really before the first large deep sky catalogue, and it's all sky both hemispheres, before the photography was used. And a lot of the objects in it were discovered by the Herschel family. William Herschel and his son John Herschel travelled to Cape Town, and they did their surveys. It wasn't just amateur pointing around. They did a systematic survey. They had their telescope lined up so it could only swivel north and south, and they just changed the declination and then waited for things to drift past. And so they ended up over a long period of time scanning the entire sky, visible from Slough outside of London, or near Windsor Castle actually, was where William Herschel lived, and his son extended the work into the southern sky from Cape Town. And when photography came along, they started discovering a lot more objects. So the index catalogue was added, which is mostly photographic objects. There's a few that are just ridiculous omissions from that were missed in the NGC catalogue. The reason they can't add them into the NGC catalogue because the numbering is in order of right ascension. So if you find an object between two objects in the NGC catalogue, you can't stick it in there. You'd have to call it NGC 104.5 or something like that.
The same thing happened with the Bennett catalogue. Started off with his first one, and which is also ordered in right ascension. And then he did two. Then he added stuff into it. So you've got things like Bennett 109, Bennett 109A, Bennett 1.
Yeah. So what they did for the NGC catalogue was just to publish index catalogues to extend it. But then with large telescopes and photography coming on screen, they were getting so many galaxies. They had then a special catalogue just for galaxies called the Principal Galaxies catalogue. So you'll see PGC followed by a number. And of course these days, especially with the large telescopes we have now and space, like the Sloan Digital Sky Survey and things like that, there's vastly more galaxies known now than even is in the PGC catalogue. But most of them are not a lot of use to amateurs because you need really large telescopes, even with cameras, to be able to image them. Okay, a couple of other interesting ones is the Malott catalogue, and this was just a catalogue of star clusters. Some of them are in the Messier catalogue and some of them are not, and they do go to fainter ones. And also there's a few that are just cover a larger area of the sky and weren't sort of recognised as clusters by other catalogues. So you'll see that reference. And also Barnard's catalogue of dark nebulae. And Actually, you can see quite a lot of them on the back wall there. If you see that, that's Emmett Campbell's wide-angle shot of the Milky Way. You can see quite a number of dark nebula in there, including some of the Barnard's Catalogue objects. Dark nebula are just really areas of dust and gas that obscure the stars behind them, so they look like dark patches in the Milky Way. Right, we better move on. How are we going time-wise? We started a bit late, but we've got to do...
9 o'clock now.
Yeah, we've got to do the solar system. And won't say anything really about planets. We know about them. They used sort of a Greco-Roman naming scheme for the planets. Comets and asteroids are the other objects in the Milky Way. Okay, so they originally didn't sort of have names as such. They were just sort of a particular year of an interesting event, the Great Comet of 1680. Halley's Comet is an interesting one that we'll mention because some comets are recognised as periodic because they've been observed more than once, because their orbit around the Sun brings them back within the sort of time that humans have been recording this stuff well enough to recognise that it's the same comet returning. And the first one of these was Edmund Halley, who used Newton's laws to figure out when a particular comet was going to return. He died before it actually did return, and promptly had his name ascribed to the comet, so it's called 1P Halley, meaning the first periodic comet. And of course there are quite a number of them now. But what they do for comets in general is to come up with a scheme where they have C/the year. So, and then they have a 2-letter code, and then later on it gets the name of the discoverer once it's confirmed. And so the scheme for the letters is obviously the year is the year it was discovered, and then you have the first letter corresponds to the half month. So the second half of February will be the letter D, and then you have a number which is the number of the discovery within that half month. So an example, does anyone actually see this comet, C2006 P1 McNaught? I did. It was easily visible in the twilight sky to the naked eye. Yeah, there's quite a lot of pictures of it on the internet. It was a really good comet for the southern hemisphere. We we've had them since, but nothing as bright as this one. Like, it was easily visible in the twilight.
There's one in the northern sky that's supposed to be pretty good at the moment.
There's one that's a northern hemisphere one though.
That might explain it.
Yeah. Swan, isn't it?
Yeah.
There was another one for us. There was Lemon and Swan. Lemon is the northern hemisphere one, is it? Yeah. Yeah.
And Swan is in the evening sky.
Yeah, it's in the Milky Way right now.
Yeah, just past the Lagoon Nebula, apparently.
Yeah.
Okay.
I wouldn't mind some clear sky after.
Yeah, you need a clear, clear evening sky to be able to have a chance.
Mm-hmm.
Yeah.
Okay, and then asteroids, kind of a similar scheme. They're given a provisional year and get another sort of a half month and a letter order. And then once they're confirmed, they get given a number. So, for example, there's a few given here. Oh, the first one known was given the name Ceres, and it's number 1 because it was the first asteroid discovered. And you can see some listed here that the first 3 were discovered at this observatory here. So you have 19620 Auckland, 23966 Maunga, which is named after the Maunga here, and 23990 Springsteen. Now those three were discovered by Ian Griffin, who was the manager of this place around year 2000-ish. He's now the director of the Otago Museum, but he was a keen asteroid hunter. And then the latest one there, you see 386622 New Zealand. That was discovered by Jenny McCormick out at Farm Cove. And she decided, well, there was no asteroid that had been named after New Zealand, so that's what she's proposed. So as a discoverer, you get to propose a name, and as long as it doesn't offend anyone, then the IAU will usually accept it. Okay. We come to the last type of object, and this is something that's been in the news recently. I forgot I hadn't updated the slide because we've got a new one on the list now. These are interstellar objects. So these appear to be like comets or asteroids, but they're detected in the solar system, but they're going way too fast to be possibly having anything to do with the solar system. They only come zipping in, zip straight back out, and the sun doesn't have enough gravity to stop them. They're in what are called a hyperbolic orbit. The first one there is one eye. The I is for interstellar, Oumuamua, which is Hawaiian name that was given, which I believe means a visitor coming from afar. And then the second one, Tuai Borisov, was named after the discoverer. And we have the reason that was given a personal name because one eye is an asteroid, whereas 2I is actually a comet, so the discoverer got his name attached to it. And there's a third one which is also identified as a comet, 3I Atlas, currently passing through the solar system as we speak. A lot of speculation. There was somebody claiming it was an alien spaceship.
Most of the things I'm reading about...
But it is very unusual because the outgassing isn't like the typical sort of comets that have been observed before. But then we haven't observed many interstellar comets, and it's believed that it's very, very ancient, much older than the solar system. So it probably formed in a very different chemical environment to the objects in the solar system. So I think that's the finish of the presentation. So any questions or comments?
About 3I Atlas, it was basically composed of nickel.
Okay, well that's interesting.
Yeah.
You wouldn't expect something with a lot of nickel in it to have a lot of volatile material.
Yeah.
So that's kind of interesting.
Well, a lot of stuff that I've seen about Atlas, I'm sort of taking with a grain of salt.
Oh yeah, there's some ridiculous stuff out there about it as well.
So if you know with the Vera Rubin Observatory discovering many bodies in the solar system, big asteroids.
Yeah.
How the heck is keeping track of all of it?
Well, yeah, the job of keeping track of them is the Minor Planet Centre at Harvard University, and that's basically all they do. Is, in fact, they publish a list of asteroids they would like observed, because they calculate the orbits, but the orbits get perturbed a little bit, and if they don't get reobserved, they can lose track of them. And this is probably going to become more and more of a problem with the Vera Rubin Observatory, which is going to add a few million of these objects pretty quickly, and keeping track of them is going to be okay while the Vera Rubin is scanning the sky, but I believe it's only going to run for 5 years, and then after that I suspect a lot of these objects will get lost.
What are they going to do with it afterwards? Big observatory.
I don't know. I think they just, well, to run it longer they would need funding, I think, is the issue.
Sure.
They've only got funding for 5 years, I think, is the bottom line. Oh, we've got
Didn't,
we've got
Musk
Starry
test-
Night from
didn't Musk-
Vincent van Gogh.
I was just gonna, didn't Musk Tesla end up with an asteroid number?
Oh, possibly the one that he fired into space.
Yeah.
Yeah, well, we just heard there's going to be another BHT lecture next year, and the topic of the lady is actually, I believe, moving to the University of Canterbury from overseas, but before she starts her job, she's going to do a BHT tour, and I think her talk topic is something astronomers versus billionaires, and I think it's very much aimed at Elon Musk.
Oh, that's gonna be satellite light pollution.
Yeah.
Oh, the number of pictures. I was going through some pictures that I got with the SLU telescopes, and a lot of them are getting photobombed by satellites.
Oh yeah, especially if you image in the first couple of hours after sunset or the first couple of hours before dawn. We'll see that even in the meteor cameras that we've got out at QMU. They get heaps and heaps of satellites in the crossing through the field of view, spoiling everything. But I guess if you want internet from rural areas, it actually